We are going to build this hydraulic model in EPNET.js using real GIS data and go through the process of cleaning it up, getting it running for 24 hours, and showing how you can use the tools in EPNET.js to build hydraulic models quickly and more easily than you can with the traditional tools. To start, you can go straight to epnetjs.com. From here, you can click Launch EPNET.js. You're going to see this welcome screen. What you want to do is click Import from GIS. Here, the first thing you're going to choose is your model settings. For us, this model is based in Tasmania, Australia, and they use metric. So I'm going to do the metric unit system with liters per second with Hazen Williams as the headless formula. Next, we need to import the GIS data. So I've already prepared this GIS data. The main thing you need to do is to filter any like abandoned assets or things that you don't need in the model. And then we can select the corresponding element type for each GIS file. So for the tanks, we'll pick tanks. For the water mains, we'll choose pipes. And for the water treatment works, we'll pick a reservoir. You can see those have been assigned here on this preview map. Next, we're going to map the attributes. So the first thing we'll choose is the ID. We'll choose the facility ID. You'll see that it will populate down here as a preview, so you know what you're applying. After that, we'll do diameter for the pipes. You can see they've come here. And material, and then the year as well. I believe it, if we scroll down, we should be able to see the full list. And we'll double check what it is. Install date here, and you can confirm that it is correct, and it comes down here. Next, you can also choose custom attributes. So if there is certain custom attributes that you want to add in, you can select them here and they will be also imported. There's no custom attributes that I need for this model, but if there is something of value, you can include them at this stage. We'll do the same for the tanks. I'm just going to include the ID here. So the facility ID, or if you find something more useful, for example, here maybe MX location is more useful, we can swap it here. And I'll do the same thing, MX location here as well. So we have the pipes, tanks, and reservoir, the attributes set. Now we're going to build model. And that quite quickly went through the process of linking and connecting all the model elements together. So if we have a quick look at the map, you'll see all the intersections have been joined together. All the attributes have come in. And it's also set the elevations as well. So we have a global DTM that has applied those elevation values. Now, if we tried to run the model, it would not work. There are a few attributes and settings we still need to do, but you can try pressing simulate here and you'll see it's found a certain amount of issues. You can try to run it. It will most likely give you an error from EPNET, or you can do fix issues first. If you click fix issues first, it's going to highlight a couple of the attributes it's found. So for example, the tank minimum level is missing. There's some pipe roughness missing as well. We can actually click back here, and there's a couple of other tools as well that we can use to help clean up the data. You can see this network review panel. You can access it here on the left with this toggle button located up on the top right hand side. Now, there's a couple of tools that you'll want to go through to make sure everything is correct. Usually the first thing you want to do is make sure this network is fully interconnected as one connected network. And it's useful to use the connectivity trace to do this. You can see we have a range of subnetworks and they all indicate they have no supply source. If we select this one, you'll see that it has selected the majority of the network, but we can identify some areas where it isn't connected. If we select this one, we can see there's an isolated section down here. If we zoom in, we can identify quite quickly that there is a gap. Now, if you want to connect these two junctions or these pipes together, all you need to do is click and drag and then drop it on top of the other junction and it will merge it all together. So then you'll have one interconnected network at this location. We can continue working through these areas. If we select this 9, you can sort of see this is where our tank is, and these are actually drainage pipes, so we don't need these in the model. We can come over here to this asset panel and click delete, and we can remove those. Next, we have this section here, which is actually the main that is used to pump up from all the treatment works into the tank. We're going to connect this one in. We can drag it across here. And then we can come up to the other side and we can see that there are two sets of mains. So we'll connect this one here and this one here. And now there's a couple of small sections of some miscellaneous pipes. This obviously, I'm not sure what this is. This probably doesn't have any value. We can delete it. Same here. Maybe this is probably another drainage pipe that's not necessary in the model. And then once again, another miscellaneous pipe around the tank that we can get rid of. At this stage, we now have one interconnected network, which is what we like. We have connected the reservoir to the tank. This is at a lower elevation. We can see 162 versus 237. So we need to be able to pump up from the treatment works into the tank. So what we're going to do is we're going to add a pump at this location. You can see a toolbar across here that allows us to add elements and draw them in. This one here is the pump. If we want to split in a pump, all we have to do is, you can see as we hover over the pipe, we can see where it's going to connect. We can click the first part of the junction in on the pipe and then next. And EbNet.js has cut and snapped in that pump automatically for us. There is a few design attributes we can put here on the pump curve. I'm just going to fill this in with dummy information. I'll just say 1 and 1 for now, but I'll also turn it off, and we will run the system just under gravity to start with, and we'll come back and design this shortly. We can now check some of the other tools. There's no orphan assets, so nothing here. These are, if there were junctions or other assets not connected to the network, so we don't have to worry about this one. We also have the proximity check. And what the proximity check is looking for is for pipes that are overshooting or undershooting connections. And so, for example, if we click here, you can sort of see from a distance, this looks like it's connected properly. But if we zoom in, we can see that it's actually not fully connected. There's a gap here, right? So if we want the network to perform as it is in real life, we want to make sure these connections are correct. So we can select here, and this will connect this location. EbNet.js does come through and try to connect everything within a certain tolerance, but you can choose here to expand that tolerance and confirm that things are matching. So we can check in this one. And in this case, you can see this is actually the main that comes up to the tank. And if we zoom in, this is just a coincidence that there is a junction at this location. We don't actually want to connect the that pumping main to the distribution network. So we can ignore that. And the rest of these are not of interest. They just junctions sort of close by on short lengths of pipe. But at this stage, we can say that there are no pipes with connectivity issues. At this point, we're pretty close to being able to run the network. If we try to run it now, Ethernet will also warn us about some other issues. So we're saying 338 issues. We can press fix issues first. And once again, it will bring us back to this panel that we saw before. So a couple of things we need to set up. The tank, maybe we'll start first. It's saying that there is a missing minimum volume. So we're going to say it is also coming with some default levels, which we can adjust as well. Here, if we go to satellite view, this tank is about 25 meters it is about 5 meters high with a diameter of about 25, and it's directly on the ground with 0 volume. And you can see here it's calculated, it has about 2.5 megaliters automatically, lets you know here. You can also define it by the total volume or volume curve as you need. You can see we've also got a warning here that this initial level is higher than the level. So we can change this and we can make this 4.5 meters. Lastly, we have just saying that the pipe roughnesses are missing. We can see we have the material in the year, but no roughness coefficients. We can see if we come to the data table, which we can pop up with the bottom panel from here and go to pipes, we can see we are missing all the roughness, which is a required field. If you select here, they'll list each of the assets. Now, generally, you will assign a initial roughness value based off the material and the age. And we also have tools to help you do this. within up here on the tool panel, we have the operational data and we have the pipe library. The pipe library is a list of materials and corresponding roughness coefficients for those pipes. We can import the existing materials from the model by clicking import and then import from model. And we can see now we have a list of all the different materials and the years. This network was obviously built about 60 years ago, and you can see that it has assigned those values here. If there were more variants, you would see more numbers here. You can obviously come through and change these values as you see fit. So you put 130 for sort of the older asbestos, and then maybe, you know, PVC we can leave slightly more smooth. You can export this out into Excel or CSV, update them and import them in with the values that you need and reuse those. We can save this now. And what we're going to find is that those values are automatically applied as defaults to the pipes in the model, right? So we can see here, this pipe has a default value of 140. If we wanted to override it for calibration, we just put a new value on top and you'll see that has come through, or we can delete it, it comes back. Now, if we go back to our model attributes in the network review, you can still see that there are a few pipes that are missing values here, right? We can see that they have, so PVCO, but with no year, and so it doesn't have a value. There are a couple ways that we can fix this. The first one with this, say PVCO, we can assume that all plastic pipes maybe have the same roughness. So to clean this up, we can go back to the pipe library and then just remove this row. And then if there is just a single value, it will apply automatically in here. And once again, we can see that there are a couple other values here that need to be filled in. Once again, PVC, we can fix this up by going into here and just removing these corresponding values. And then for these, you know, it would probably be worthwhile coming through and confirming what the materials are and the roughnesses. I will just apply a very smooth value of 140 on here just to get this model running. And then the same with this one. And at this point, it's saying there's no more issues in the model here. And we should have enough to actually get this model to run. So I'm going to close this down. And then what we'll try to do is press simulate. We can see that the model has simulated correctly. If we go to the report, you can see it is balanced. Sometimes it won't balance if you don't have demand. So just be aware of that. It might not be able to come to a solution. And now we can start to visualize some of the results. If we select a junction, we can see the pressures, the pipe, we can see the flows. There's no flows because we've added no demand. But we can come to this map tab and start to look at, you know, the pressures. Because we have the elevations already, we can get some initial suggestions of the pressures within the system. For links, we can see the flow. There's essentially no flow in the system, so we don't see anything useful. The next step, what we want to do is to look at applying some demand. So we have some realistic, you know, flows moving through the network. To do that, we can come up to this file toolbar option here, go import and do import customer points. And now we can import the actual customers. I'm going to drag in a customer file. And from this, we can fill in a few attributes. For example, we can do the ID, we'll do MX location. We can also pick the demand, and here we have their average demand in liters per day, or if you're in US units, it will be gallons per day. We can also override that with a default value as well. And if you're in extended period simulation, you can also pick a pattern. You can always update these later as well. I'm going to pick next. And we can either delete existing demand or add it on top. There's no demand in this model, so either option is not a problem. And here we can zoom in, we can see all the customers are in the network. However, they are not connected yet. The way that you can that this works is you can select individual customers and connect them. And we'll show you how this works. So here you can pick the pipe that it is connected to, and it will find the closest point within the pipe. Or if you hold shift, you can select the location. Say, for example, we allocate the customer to this pipe, and we select the pipe. We can now see the demand has been applied onto this pipe, and we can see the customer, and it will show what that customer connection is. And this is actually applied to the pipe, but then to the closest junction on that pipe. So if we select this one, you'll see the connected customers here. And then because of the way that Ethernet works, the demand is actually at the junctions, and this is applied directly to that junction. So it helps you understand, where these demand figures are coming from. Now, of course, you could go through and connect these all manually, but we have over 1,000 customers. It would take too long. So we have an automated process for this. What we can do is we have the allocate customer points button here in the toolbar. Now, we want to be careful not to allocate any customers to this pumping main from the treatment works to the tank. So what we're going to do is we're going to come to this tracing tool here. You can see this is a selection trace. You can right click and actually find a few more things, but we're interested in the boundary trace. And we're going to select the distribution network. You can see that's come through and selected that entire distribution network for us and avoided that main. Now this is going to be important for the allocation to make sure we're just connecting to these selected mains. So we will come to the toolbar here, do select allocate customer points. We're going to select selected pipes only. And here we can define the maximum size of the diameter that we want, the maximum distance, and we'll tell us how many allocations we have. We can see we're missing 2 here. We can edit this, add more rules, like change the maximum diameter, do different distances. And we'll just make this very large here so that we can see that we have all those customers allocated. We press apply, and now we have all those customers connected into the network, and they'll have the appropriate demand. So at this point, we should be able to press simulate. And now if we view any of these pipes, you'll see, apologies, let's switch this back to select. You'll see the actual flow moving through the network. So if we do pressure and the flow here, we'll see actual flow values and seeing the way that the actual water moves through the network. Now this is good. This is a steady state simulation, so it's a snapshot in time. We're using the average demand, so you can think this is like an average point in time on the model. However, maybe we want to do a period of simulation over 24 hours. And to do that, what we can do is come into the simulation settings up here. We can do time, and we can change the time analysis mode from steady state into extended period simulation. And we have some options here. So the total duration, the hydraulic time step, the reporting steps. At the moment it is 24 hours with a 1 hour time step. I'm going to leave it at that. That should be good for this initial values. And now if we run the simulation, you'll see a couple of things. First is that we'll have an option to view at different times. We'll see that if we come and do an element, we'll see a graph showing a change in value. In this case, it's the tank. We can see the tank level is draining down as the simulation runs. And if we click a pipe or a junction, we'll see similar values. However, there's no variance in the demand. It's the same steady demand the entire period. So that's why we get this flat line here, the same with any pressures. To make this more representative, we need to vary the demand over time. So to do that, what we're going to do is we're going to grab the some patterns and apply them to our customers. So from up here in the toolbar, we have the operational data, and we're going to do patterns. We're going to add a residential pattern. I'm going to call it res. And here we just need to paste in a pattern. I'm going to grab a pattern from another model, and then we can apply that directly in here. You can also come into something like Excel and grab this, but I'm just going to grab this from another model. And I'm just going to copy and paste this value in. See, copy and paste some values, and these will be multipliers at different time periods. So they'll take that average value of 1 and bring it either down or up. And you see we have a peaking factor of about 1.7, both in the morning and the evening. We can save this. And now we need to come through and actually change each of these customer points to use this new pattern. So what we can do is we can go to the bottom panel here. We can go customer points, and we can see we're having a constant pattern. We want to change this to the residential. And now if we want to do this quickly, we can just select here, Control C. I'm going to select the top, the entire column and paste. And you can see it has placed it down across the entire, all the customer points in one go. So now when we run this simulation, let's run it. We should see, if we choose a pipe here, the flow, we can see the flow is changing over time. We can also get a slightly larger graph view by clicking up here. And you can see over the 24-hour period, the demand changing. We can also select a junction here and then view the results. We can sort of see as the tank is going down, the pressure is dropping, but we can also see some bumps as the demand changes over time. We've almost finished this model now. The last thing we need to do is set it up so that there is some controls for this tank. What we're going to do is configure this pump to work, both make sure it has appropriate pump size and that the controls work. For this, we can see just upstream of the tank has about 10 meters of pressure. And what we're going to do is we're going to calculate what the head difference between what the pump has and what the tank is to figure out how much head we need to add to get up to the tank. We can see here, if we select the elevation, we can see it's about 237. So 237.3, and we'll add 5 meters. That means the total HGL for this tank is 242.3. And we need to raise it from the head from just before the pump. So we'll take away 172.7. So we're looking at this head value here. And then that will give us, we need to raise the head by about 70 meters. So if we select in here, we can say, okay, we need to raise the head 70 meters. And we need to know what design flow. So we probably want to be pumping slightly more than the average demand. If we have a look at the flow out, so let's say, okay, maybe it's about 7.5. So maybe if we pump it 10 liters a second, we'll definitely be able to fill that tank. So we are going to raise the head by 70 to get up above that tank. And then we're going to pump at 10 liters a second. And just to test it, we'll just change the initial status from off to on. So now the pump will run for the full 24 hours. We run this, we can see it is successful. And we look at the flow, we can see it's roughly about 10 liters a second, obviously changing as the tank level changes, but that looks correct. And if we look at the corresponding tank level, we'll see that that is now coming up and getting close to full. So we want to add some controls here to avoid it overfilling. And what we'll do is maybe we'll set it up to fill at about 4.7 and then turn back on at 4.4. Now, what we'll do is we can come down to this pump here and we can activate a control. We can say, okay, we want to have level-based controls. We can choose the tank. This is the only tank here. And we said, okay, 4.7, 4.4, the pump will turn on at full speed and we'll turn off the pump at 4.7. And then if we run this now, we should see, yes, we'll see that the pump starts on, it turns off and then turns on. And then if we look at the tank, we should see that comes on and off, right? It comes down and then we'll come back on. And if, say, for example, we run the simulation for slightly longer just to confirm that it is cycling nicely, we can do 3 days, save, run the simulation. So it'll come through and you can see the tank level is there now cycling. For example, we could also multi-select by clicking, say, a pipe and then also the tank. And now we can graph both elements and we can see quite clearly the tank comes up as the pump is on, it's off, it comes down, and it will cycle on and off like that. And if we now look at, say, the pressures at any location, we can see that it's cycling nicely as you go. So at this point, I think this model is built and running very quickly. Within about 30 minutes, we have taken raw GIS information, cleaned it up, got it running, got it to an extended period simulation. At this point, you could look at things like scenarios, you could try to look at optimizing it, you could do water quality, but hopefully you can follow through these steps and repeat it. If you look in the comments below, we will have links to these GIS files so you can replicate it yourself. Thank you for following along. Keep watching out for more of these videos. We're going to build more networks and show you different ways to use EPNet.js, both to build models, run simulations, and understand your network better. Thank you.